I hope all of you are able to hear me. So today I am going to talk about the chemical engineering role for constructing our sustainable future. This is because of Elijah's invitation. He is my favorite student. He was my favorite student in the class. And when he said, would you like to talk to us? And I couldn't say no to him because he was my favorite. So without further ado, I would like to talk about the only sustainable aspect that we are studying in our group. We do multiple things, as Ryan mentioned, lithium ion, sodium ion, and potassium ion batteries. But I am taking only 5% of the work and demonstrating here in next 35 minutes or so. So this is my group. They are graduate students, postgraduate student, namely postdoctoral researcher, and some of them are scientists. So it is really a diverse group where we do multiple things. In addition to our civilians, we also train defense folks in our laboratory. And the reason is we are mostly supported by DOE, Department of Energy, National Science Foundation, Navy, Army, NASA, and so forth and so on. So we also train their people. They take the knowledge back on the sustainability side as well as energy storage side, and then implement to their day-to-day work, eventually helping out our society. So outline of this talk is very simple, straightforward, where we will be talking about green processing. What could be the greenest way that can take something totally valueless? And you will see what are the examples for that. And then we make something really valuable out of it. Being a chemical engineering students and faculties, you know that if you sit any place and you see around, there are so many problems. So how can we solve those problems in a reliable way where you develop a process that is low cost, very effective, and sustains, means, again, there is no scarcity of anything. We have abundance of that byproduct or the initial precursor that you are going to use. We will be also talking about what are the battery research challenges, and in order to solve that, how we can put it together, the materials you developed that can be utilized in batteries. We have many other applications, but today we will only focus on the battery side. And then we will elaborate on few examples that the material we made from the sustainable way and directly goes and sits in your lithium-ion battery that is in your cell phone, laptops, electric vehicles, and so forth and so on. The process we develop, we call it as upcycling. And upcycling is nothing but you take something totally valueless and make things which are highly valuable for the society. So we will focus on this upcycling phenomena. That was the word I started using like almost 10 to 15 years ago. And nowadays it became very famous because everybody wants to take valueless things and make things valuable out of it. So we will answer only 3 questions today. Next 30 minutes, 3 questions, and that's all. If you take a packing peanut that you can see here, being a chemical engineer, you know that they comes in a variety of boxes. You buy laptop, you buy electronics, or you buy chemicals. For the research work, you get a packing peanut, something of this order, which has a cushion effect. So if you have a chemical and around that, if there is a cushion, there is no vibration during the transportation. Eventually, the goods that you want to have can be transported safely to you. So one of the work when I joined 6 years ago at Purdue, we carried out that is packing peanut upcycling. As you know that we really throw away all that thing, but it has unique properties that already sitting inside. We just want to know how to extract them. You go to any grocery shops, you get hundreds of bags. Go to Walmart or any shops, all your goods is stored in the plastic bags. What you do is you come home and throw it away. And you don't know who is going to take care of it. But we can deal with that, and we can make such a unique product that can be useful. Very recent work, we were focusing on polyethylene terephthalate bottles, that is your water bottles, Coke bottles. As we know that we generate them very effectively, but we do not know how to get rid of it. Initially, if you know or not, we used to take polyethylene bottles and send it to China for recycling. So even we do not have any systematic way here to recycle polyethylene bottles. So you just imagine how dangerous it could be for the earth, where such polymers or plastic waste is created daily basis, and really we have a hard time to recycle or upcycle it. So you will be seeing what process we develop, how effective it is, and what can we do with the product we fabricated out of it. So a little bit introduction to my group. We do focus on a variety of battery technologies that includes lithium ion, that is typically in your cell phone and all electronic devices. Those are the batteries sitting now. There are next generation batteries such as sodium ion batteries. Sodium is much more sustainable compared to lithium. Lithium is really a scarce element on the earth crust. And because of that, the batteries are expensive. As you know that your cell phone battery try to die after 2 to 3 years. So instead of changing the battery, you try to change cell phone itself because battery is expensive. So we are working on the next generation batteries, that is sodium, that could be very good for your renewable energy storage. That includes the energy you generate from the wind or solar cell. We have to store that very effectively in an economic fashion. So the sodium ion technology is very useful. We are going beyond and also studying the potassium that is beneath the sodium in the periodic table. And those batteries are also getting studied in our group. Now, apart from everything, all advancement happening, our batteries are still discharging somewhat in the afternoon because we play videos. We do listen nowadays talks on the phone. So there is a consumption of battery very effectively. So we develop a lithium sulfur battery that has 3 to 5 times higher energy density. So if this battery can work, we can have the batteries. You don't have to charge every day. We might wait for a few days. That much energy density we have, but then it comes with its own problem, and we have to mitigate some of those problems. So giving a little bit background about batteries, there are 2 kinds of batteries that typically we have. The AA batteries, AAA batteries that you find in the shops, and you put it in the different electronic devices. Those are primary batteries. Primary means only one time, those are already charged, you discharge them, and then you have to throw them away. For example, there is a wall clock. There is a battery located that power of that clock, and within few minutes it discharges and you have to change the battery. So you are not supposed to charge that battery. Never put that battery inside the charger and try to charge it. Otherwise, there is a possibility it could explode because the battery is not made to charge or recharge. On the contrary, there are rechargeable batteries. That is in your cell phone, we are allowed to charge and discharge, let's say 1,000 times. With some capacity fade with timing. So those 2 types of batteries. So we will be just talking about the secondary batteries made from the material that is upcycled from the trashed material. Now, why lithium-ion batteries are important? Because the lithium is the first element after hydrogen on the top left, which is light in weight. So we can store a lot of energy in the lighter material, and that's why it can sit in your cell phone where the energy density is enough high and it is also not heavy. We get many other advantages with this lithium-ion battery. That's why it is very important to work on that and make it better and better. However, it also has some issues. Sometimes batteries can catch fire because of the flammable electrolyte sitting inside. And the typical life of battery is really short, 3 to 5 years now. And our dream is to make batteries that is staying in your electric vehicle, let's say for 15 years. So we have to work on that too. Little bit history on the batteries. There are few American scientists who are pioneer to develop this battery technology. So Professor Goodenough in Texas, Austin, he was a pioneer. In 1980s, he developed lithium cobalt oxide based cathode. Also Whittingham from New York developed cathode material. And then Sony was the first company to bring the lithium-ion batteries to us in 1991. So this technology is only 30 years old, and now it is everywhere in the Chevy Bolt, as well as Tesla, and it's really everywhere. When I used to work at Argonne National Lab, that time our former president visited us and really made a striking statement that we should not trade our dependence on foreign oil to a dependence on foreign batteries. As you know that most of the batteries are imported from various countries that include South Korea, Japan, China, and we are enjoying all those batteries. So we should create our own batteries in the United States because there is a huge need for the global population. So giving an idea that 3 people got a Nobel Prize in chemistry in 2019 for this battery technology. And this is really remarkable to see that the development happened in 1970s and 80s, but it took them almost 25 to 30 years to get a Nobel Prize because that technology showed up in everybody's pocket and purses. So there is a small question. Since you will be answering asking the question later, I will answer myself. If you have a Tesla, if you see that the whole Tesla, the whole chassis is made up of batteries. And there are thousands of small batteries that AA cell kind of thing. It is engineering name is 18650. That means it is 18 millimeter diameter, 65 millimeter tall, and it is a cylindrical shape. That's why this battery is called as 18650. All Tesla batteries are made up of Panasonic, a Japanese company. So the technology goes inside the Tesla electric vehicle is from Panasonic. And we are using up to 9,000 cells or batteries, they stick together, and that can drive you up to 300 miles per charge. But you see that we have to do so much engineering in order to put all those batteries together, charge them together. Some of the battery may not charge. Some of the batteries could discharge faster. So it's really complicated things. Batteries are also very sensitive to the temperature. So we have to be very careful how fast we are charging and discharging and what temperature we are operating the battery. So the whole battery pack is sit inside this cooling system where the pack temperature does not really freeze or go to too high temperature. So there is a complicated electrochemistry and chemistry and chemical engineering happening inside this Tesla, and it has a huge amount of energy. So battery has to be safe, otherwise exactly you are sitting on the top of this battery, which can be really dangerous once it is in the charge form, can release a huge amount of energy, and it can be terrible thing. You might have already seen some of the videos where the Tesla is on fire and then nobody knows how to mitigate that fire because it has so much energy. Until the whole energy is consumed, it just go on having the fire. So how can we make the material for such technology that is sustainable? Now, these are the challenges. The cost of the batteries is very high. If we are sustainable, we can get hold of this one. The batteries are not safe. We have to make them safer. We have some ideas how can we make them safer than today. The life of the battery is really limited. We want to extend it. The limited life comes from your chemical engineering. The organic electrolyte sit inside the battery, which is a liquid, which has pH 2. That means it is highly acidic. Anything from the periodic table, you put it next to this acid, it has a tendency to corrode. And because of that corrosion, the life of the batteries is very small. Either you use the battery or you do not use. Now the weather outside is really terrible. It's cold. So the battery really does not like cold weather. There could be a cold cranking. The lithium dendrites could be fabricating. And also it does not like very high temperature. More than that, now recycling became another problem for batteries. Namely, we are 7.77 billion population on this earth today, and we already have 15 billion batteries that is outside. So we have to really take care of all the challenges together. Otherwise, our future will look like this broken glass, because we are handling one challenge and not worrying about the recycling and other aspect. So it is very important that you concisely think together in order to solve those challenges in one part and develop a technology. So let's start talking about a little bit synthesis processes and engineering that we use. There are processes inside, within the society they do use today in order to make the battery material. For example, solid state chemistry is used to make the cathode material at very high temperature. Cathode is a positive electrode in your battery. There is a mechanochemical milling kind of things happening, which is also consuming a lot of energy. So all these processes have some disadvantages. Also that includes the precursor, which could be expensive. So one of the technology I was telling you that we developed, that we call it as trash to treasure approach. Really, we took a material that is useless, you're throwing it out, it is a burden on the earth, it can stay up to a few hundred years. If it is polystyrene based, it doesn't want to decompose, it can just stay there. So we developed a process that could convert in a short time these trashed packing peanuts to this dark black powder that is graphite, or a carbon powder, that can act as a negative electrode for your battery, and it can reversibly store the energy, namely it can charge and discharge. So that is the technology we developed at Purdue very recently, and which has a great future as everybody wants to make a sustainable material and utilize it for different purposes. The batteries are working, as you can see, that those are the small battery we make in the beginning, and that can power LED and many other equipment. So the uniqueness of this carbon is, it has a unique structure because of its porous architecture that has a cushion effect. As such, we took this starch-based packing peanut, and then we converted into carbonaceous material just by heat treatment in an inert atmosphere around 600 degrees Celsius. It produced very unique type of carbon where the sheet diameter is up to 1 micron, and the thickness of the plate, and then the width of the plate is several micron long. Such carbon has many other applications, not only in the batteries, but many other. One can capture the carbon dioxide that you generate just by tailoring the pore diameter of the carbon. It can act as a conducting additive. You are printing all the time, so it can use as a printer toner ink that you can see with your eyes. All your car tires are black because they are utilizing carbon as a conducting material to dissipate the heat into the atmosphere. You have filtration technology where we use the carbon. So there are a list of application of such carbon that you simply derive from the waste material. Otherwise, you have to take hydrocarbons, just like a petroleum gases, to make the carbonaceous material. Then we characterize to understand exactly what is happening. So this is a Raman spectroscopy, which tells you what kind of carbon you have fabricated. And it tells that it is a disordered form of carbon fabricated at a lower temperature. This was the original packing peanut Raman spectra that has many bonds, the bonds coming from the stretching frequency. And that's why we have multiple peaks here. But eventually it modified into only simple 2 peaks. That is a signature of graphite. It has a huge loss because starch has most of water and around 28% solid. So we remove the water at lower temperature, and this is the solid material we have left over that we use in our technology. Now, this might be too much for you, but I will simplify and let you know that this is battery performance. These are the different temperature, 500 to 900 degrees Celsius we utilize to make the carbonaceous material. And then you can see that battery is charging and discharging very nicely. So this is a cycle number and this is a capacity. The typical capacity of the graphite is 372 milliamp hour per gram. Actually, we are getting even higher capacity when your charging and discharging rate is slightly slower, up to 10 hours. That means this material is not only behaving like a standard graphite, but even better than that because of its unique architecture. This plot explains the rate studies. Namely, if you even use 1 hour to charge and 1 hour to discharge battery, you still get very nice capacity. On the contrary, the standard commercial carbon gives you very small charging at fast charging rate. But this is behaving good because of that thin sheet which can charge and discharge very rapidly. This is impedance spectroscopy that is important to know that this does not have too much resistance in the system. So commercial carbon has this bigger semicircle versus this packing peanut derived carbon has a small. So there are plenty of advantages. Those batteries were cycle, charge, discharge, and finally we open them and find out what happened to the sheets that we put it inside the battery. Did they disintegrate or whatever happened to them? This is the original material, put it inside the battery in presence of some binder because we have to hold them together. And after cycling, after aging the battery, the sheets are there. And that means the packing peanut derived sustainable material is robust enough to survive inside the battery. And then we did some characterization to understand that the structure also did not change. So morphology is the same, structure is the same. There is a small additional peak that is because of the electrolyte decomposition happened inside the battery. So as such, we can say that those batteries are really doing good and not having any trouble. Now I was talking about the sustainable batteries, that is a sodium ion battery. So this material is very good for the sodium ion batteries, which will be slightly bigger batteries than your lithium ion battery, as sodium is bigger molecule or bigger element in the periodic table. So this is a typical charge discharge cycle happen. You have a typical cathode. During the charging, you bring the lithium inside, those disordered structure, and during the discharge, it goes back, and it happens reversibly. As long as it is happening, your battery is operational. So having the unique properties of this carbon, we wanted to use it for sodium ion technology. So there is a company in United Kingdom called as Ferradion. They design these bigger size batteries. We call it as pouch cell. This is the cell sitting in your cell phone because cell phone is a flat prismatic structure. The AA batteries doesn't fit inside. So we have to make a flat battery that goes inside the space available, and then the device remains the small. So we made the bigger size battery that also gives you higher current. And again, you can see that we started with packing peanut. This is a scalable process. We don't need anything sophisticated, and eventually we can make the batteries. And it can cycle for hundreds of times with very limited capacity fade. The Coulombic efficiency, that means amount of sodium you put it in and you extract back, it is almost 100%. So there are many advantages to use this sodium ion technology. And really good things started happening. This is a typical charge discharge plateau for sodium ion batteries. You might recall who is this person. Your Purdue president visited the lab to see what's going on here, where we are developing some sustainable technology. As you can see that we started with packing peanuts. We made it a bigger scale, and eventually in the industrial scale, you need large amount of material. There is a company in Tennessee who helped us to scale this up, and eventually the batteries are becoming in a larger scale. With some fine tuning, this technology could become commercialized at some point. We used chemical engineering knowledge, and we decided if we use this and scale it up, Is there any environmental impact? Are we releasing some of the carbon particle to the atmosphere that we are not able to see? And indeed, some of the particles were going out. So we decided to capture them back and feed it back to the system in a way that we do not release anything to the environment, keeping the environment as clean as possible. There is a video which is available on YouTube. If you want to watch now, I am happy to show you that. That explains the whole process. Does it want to run? I think I will save the time. You watch the YouTube video that comes under my name and Purdue. That did explains that how is the whole technology developed and how it is useful. There is other technology that I wanted to shine a little bit light on that. That is based on the plastic bags. So far we were talking about recycled packing peanut. Now we will talk about the bags. What can you do with the bags? And then we will touch base to the bottles. So that way we are really thinking about sustainable science and technology that chemical engineers can handle. So you take these bags, those are two kinds, high density polyethylene and low density polyethylene, and make a unique material within a minute. So we have developed a reactor that can make a unique form of this carbon, which is completely spherical solid bodies. Actually, each and every particle is completely spherical. Carbon is a two-dimensional material, hexagonal structure. It never wanted to become spherical, but this technology could make it. If you are a little bit generous, we can throw some catalyst. You might have heard the catalyst that many chemical engineers are using. This is a cobalt acetate bottle. If you put a small pinch of that, you can grow the carbon nanotubes out of it. There is a Nova Science video on YouTube. You can watch how we grow the carbon nanotubes out of these plastic bags in presence of catalyst at higher temperature. So really a unique technique which can remediate plastic bags effectively. So one of the things again related to batteries, we wanted to make a spherical form of carbon. This is the best carbon one can make today with other processes. We call it as mesocarbon microbits, which is really expensive. And the reason is this carbon is heat treated to 2800 degrees Celsius for longer time. So you put a lot of heat to make such carbon. And we could make the carbon completely spherical, more spherical than this one. And within a minute, because of the safety aspect, batteries could become very safe when you have a spherical particle inside the battery compared to irregular shape, something like this. And I will show some of the data on that. The physical properties are very important. The surface area has to be small, and that's why it is potato shape and slightly bigger particle. We also have very similar properties in order to really implement this material into technology. So this is the reactor I developed during my research myself at Argonne National Lab, where it is considered as high temperature, high pressure reactor in order to make such unique material, and which has plenty of advantages instead of disadvantages. It is a single step process. Anybody can make it. You don't need a PhD to make the material. I don't use any solvent. Chemical engineering is known to use solvent and alcohols and this and that and distillation. I avoided everything. I just throw the plastic bag inside and heat it up and get the product as we need. We get a dry product, so we don't need to do any further processing or purification steps. We keep it environmentally benign because we do not release anything to the atmosphere. Everything is sealed and controlled, as you can see in this developed reactor. So there are advantages to use this process versus all other. This process can hold up to 2000 PSI pressure. So this material is grown under the pressure. The reactor could hold up to 800 degrees Celsius temperature, and the size of the reactor was 80 cubic centimeter. So we made this plastic bag to carbon product, and we did very systematic X-ray in order to figure out what kind of product we are getting and when we are getting it. So we came to know that during the cooling system, we get this carbon And that's what this X-ray is talking about. It has a very unique capabilities. It is completely spherical. Actually, you put the atoms together and make something spherical. Only the nature can do it. It is very difficult to do it ourselves, but this process could do it. So again, there is a beautiful structure evolving when we are heating it to higher temperature. So we made it from the waste, and the batteries are working. As you can see that the full cell battery that has a unique cathode and anode, hundreds of cycles it is giving you without any problem. I was talking about the safety. It can make the batteries safer, and this is the evidence for that. The spherical carbon can generate some heat during the overcharging and thermal runaway of the battery, which is a small number compared to your graphite that is sitting today in your cell phone. So that heat generation is very high, almost double, up to 200 degrees Celsius. This convinces that this can make really the battery safer where the material is used in a sustainable way. This technology won R&D 100 award in 2015. Namely, they choose only 100 technology around the globe to figure out which are the best for that particular year. And this technology was chosen based on that. Elijah, how much time I have? Few more minutes?
A few more minutes. We're planning on 3 more minutes.
Okay. So this is the second technique I showed you, and you guys can go watch those NOAA video. There is a TED Talk and many other news channels on YouTube. You can watch there, so we can save some time. So last thing I wanted to show that we took your plastic bottle that is made up of polyethylene terephthalate, and within a minute, we put it in the microwave, specially designed microwave, that makes these beautiful flowers out of polyethylene. And the process is so simple. You take it, you put it in the ethylene glycol and put it in the microwave, heat it up. The ethylene glycol reacts with polyethylene terephthalate, makes the sodium terephthalate, and those flowers are sodium terephthalate. The unique morphology you can get, just bottle is converting to bright white powder, that is sodium terephthalate. The diameter is again thin, so the battery can be charged and discharged very rapidly, and that can store the energy that you can see here. So we use it for sodium-ion battery. NIB means sodium-ion batteries and lithium-ion batteries. And we charge and discharge the batteries, and those batteries wanted to really charge and discharge. As you can imagine, we started with your empty bottle, Coke bottle or water bottle. We throw it inside the microwave, and that microwave within a minute converts this material into polyethylene terephthalate. So there is a lot of patent material and publications out there if you guys wanted to figure out exactly what is happening. But the bottom line here is a so sustainable way to convert this into something useful. And this sodium terephthalate is very expensive. If you Google now, 5 grams of sodium terephthalate costs you $25. If I take one empty bottle that is around 50 grams or so, I get around 20 grams of this sodium terephthalate in a minute. And the solvent I use, that is ethylene glycol, I can repeatedly use it until it completely consumes. And there is no byproduct or anything. There is a solid powder at the bottom of reactor. You get it out, and it is a bright white powder, just like titanium powder, and it is ready to go into the technologies. So this is the last thing I wanted to showcase, that those batteries are also working. And to give you some time for the questions, I'm going to stop here and letting you know that there are 3 technologies which are all sustainable, where we started with waste material and make something treasure out of it. And there is a significant role of chemical engineering here. We need to understand the chemicals, its properties, the systems like microwave system, how does it work? How can you implement in an effective way that could help us to make a unique product with a unique process technology that can be developed with the help of chemical engineering knowledge we have, and that could benefit to the society. So with that, I am really going to thank you for listening to me. and happy to take your questions.
All righty, sounds good. Thank you very much for that presentation. So we're going to take a couple questions up until about 9:50. So our first question is, what is the safest technology, lithium ion batteries or lithium poly batteries?
So they have their own advantages and disadvantages. So lithium ion batteries are using the electrolyte that has a liquid electrolyte. It is like a soaked, let's say, sponge. So you have an anode material, cathode material, and the liquid is poured where the electrode is soaked, but still it has a liquid nature. And this electrolyte is flammable. If the battery temperature reaches to 50 degrees or above, the electrolyte breaks down, and that is the reason some of the battery catches fire. In the polymer-based electrolyte, that is lithium polymer batteries, where the electrolyte is like a toothpaste, it is a gel. So the tendency to catch battery fire is less because of that jelly nature. But then it also can suffer sometimes with a charge and discharge rate. It can be charging and discharging slowly because the lithium has to move through this polymeric matrix instead of just a liquid nature of this liquid electrolyte. So there are advantages and disadvantages. The safety-wise, the polymer battery is more safer because of the polymer nature we have as an electrolyte. So we do use both of them and develop both of them in the lab. But I would say polymer-based batteries are more safer than lithium ion.
All righty, thank you for that answer. Our next question is, what are the plans for disposal of discarded batteries or used batteries? And then what are the challenges associated with this?
This is really a unique question. I can tell you that we are generating so many batteries around the globe. Nobody has a foolproof solution yet. For example, if you get a battery, waste battery or thrown away battery, let's say from your cell phone, the material could be $1 worth inside that battery. But today we need minimum $5 to get that $1 worth material out of it. And the reason is the anode, cathode, electrolyte, and all that complex chemistry sitting inside the battery. To get out of that battery anything which is a problematic. For example, if you want to mechanically open the battery, then the electrolyte is pyrophobic. If you are putting some mechanical force, the battery can get crushed, can generate some heat, and battery can explode. So whole plant can be exploded. So how can you selectively take out that pyrophobic electrolyte from the battery, which is very difficult. People said we will put CO2 gas. CO2 and then the gas goes to the atmosphere and then we make everything contaminated. People said that we will put some acid or base, then we also generate some waste. So really there is no foolproof process. We are doing some upcycling. One of our Purdue technology, which is patented, which talk about taking this lithium cobalt oxide from the waste battery and make a lubricant out of it. So the lubricant grease that you put it in your bicycle wheel, that grease is made up of lithium hydroxide. So we took that idea and utilized this waste material to make a lubricant, which can reduce up to 85% of the friction that is happening regularly to your many places. So we call it a solid lubricant developed out of this waste material. So getting lithium out of lithium-ion battery is very difficult, not cost effective. We have to go upcycling way and find out of the box and find application, even in the concretes. One can make the roads out of it because it has cobalt. Cobalt is used, iron is used in the cement industry. So there are many people trying to put efforts to develop new technologies, but we do not have a good technology to recycle the battery. If one of you can develop it, believe me, you will be a billionaire pretty soon.
All righty. Our next question is, as the industries move away from utilizing petroleum-based plastics, will your lab's focus shift with industry to utilizing bioplastics? And then do you think the success of your research will encourage the continuation of plastic production by industry?
So first of all, chemical engineers, we have to understand what is bioplastic. Plastic, still they use the name plastic. It is having a polymeric molecule. So they take a starch and make a polymeric gel-like thing, and then they make a plastic out of it. For example, the transparent glass that you drink water with in different restaurants. So typically what happens is you can store the water into it. It doesn't degrade. That means it is really not a biodegradable one. If you Google, you will find that it needs minimum 350 degrees Celsius for some time to degrade even that bioplastic. So it is really a still plastic, although it is made from biological material or the plant-based material. But it is not the foolproof solution to your polystyrene-based plastic. Because it is still robust. It can hold the Coke. It doesn't degrade with the Coke. Otherwise, it should really degrade. Coke has pH 2, but it doesn't degrade. That means it is robust with pH and heat. So there are more and more technologies needed to get hold of our current plastic that is coming from a variety of sources, polyethylene, polystyrene. If you go to Walmart or any grocery shops, all your detergents in a plastic bottle, many things, around 30% of the things are stored in plastic now. We will never get rid of the plastic. We will still have to utilize them. What we can do is develop the process to get hold of them and upcycle effectively, making something useful product so we can utilize.
All righty, sounds good. And we've got about 2 minutes left for our last question. The question is, what does the future of electric cars mean for chemical engineers, and how widespread do you anticipate this being?
This is nice political question. I don't know how to answer that, but there will be growth with electric vehicles as people believe that this is making somewhat environment green, which is not true for your information. And the reason is when you make the batteries, you have to make so many materials to put inside the batteries. For example, the lithium cobalt oxide based cathode, where the lithium carbonate is taken from Chile mountain, that is a country in South America. That lithium carbonate is reacted with cobalt precursor at very high temperature for days, releasing a lot of CO2 to the atmosphere. And unless we release that CO2, carbon dioxide, to the atmosphere, we don't get the cathode material. So we believe that we have an electric vehicle in California and there is no gasoline or there is no carbon dioxide coming out. But when you fabricate the material, we did release the carbon dioxide. The electrolyte with similar problem. So really, when you study the whole ecosystem, it is not a foolproof chemistry that makes everything green. Even the electricity, from where the electricity is coming, including Purdue's electricity, we still burn some of the coal. So we release the CO2 there and say that electric vehicles are green, which is not true. So there will be a growth. And I do strongly feel that we should use those batteries for portable devices. There is as such no need to use the batteries inside the electric vehicle because our gasoline is as cheap as water. If you go to the grocery shop, 1 gallon of water is $1, $1.5, and 1 gallon of gasoline is $2.5. The milk is the same cost. So what is the reason that we have to put the electricity in the battery? We have the anxiety that, oh, where can I charge my battery? And where can I take my car if I am on the highway and I want to really go far away? So there will be a growth, but as such, there is no need to have all electric vehicles coming to the road because our gasoline is not that expensive. And also it is not creating that bad impact, negative impact on the environment. So the short answer is there will be a growth. Nobody can stop it because we don't understand the whole spectrum. But there will be still vehicles on the road that is powered by gasoline.
All righty. And I made a miscalculation, actually. We've got about 4 minutes left, so we can take a couple more questions. Sorry about that. One of the additional questions is, of the battery technologies that you have researched, what do you think has the greatest potential as an energy storage technology for the future?
So one of the technology that is lithium sulfur based battery that I did not show here. That is getting licensed with companies, and we got some NSF funding for that to take it to the next level, where we are generating or developing high energy density lithium metal based batteries, which are also safe. We studied the safety aspect of those batteries up to a certain extent. We also developed some sensor based technologies to keep the batteries safer and well informed to the operator in a timely fashion. Sodium ion batteries is a new technology which is taking time. As you can see that batteries were developed, the lithium ion batteries were studied back in 1960s and 70s. It took minimum 30 years to bring it to the society. 1991 was the first time. Comparatively, the sodium ion battery technology is newer. Last 10 years, we are developing it and going one step closer every day. But let's say next 5 years, you will start seeing the sodium ion batteries in the market that is powering up sustainable energy based devices. For example, the solar energy you trapped or the wind energy on I-65. There are so many windmills. Those are creating the electricity, but they don't need the electricity there. So we have to store that energy in a reasonable way with low cost. And eventually that can be utilized either in Chicago or in West Lafayette kind of area. So the sodium ion battery technology could come to the market, let's say next 5 years or so.
All righty, and we've got about 2 minutes left for our last question. Can you quickly elaborate more on the battery scale-up process and the difficulties associated with it?
Yeah, batteries are not easy to scale it up. Really complicated electrochemistry. More than that, the arrangement, and we go to the roll-to-roll manufacturing process where everything has to be very clean and neat. Batteries have organic electrolyte. It does not like the moisture. So we have to have the moisture-free room where the batteries are getting developed. On Purdue campus, we have a glow box where the moisture content is less than 2 parts per million. Oxygen level has to be also very low. Otherwise, the electrolyte decomposes and oxidizes. So that is the reason we do not have too many companies in United States are doing such a complicated stuff. There is a Tesla gigafactory in Reno, Nevada, where they do make the batteries, but all the technologies we have migrated from other countries in order to make those batteries. The battery technology is, I told you, from Japan. A lot of Korean equipment we have to buy in order to make this roll-to-roll manufacturing. In Indiana, we have a battery innovation center in Blueberry, Indiana, 2.5 hours drive from Purdue to the south. We have a collaboration with them that is supported by Department of Energy or government. But really, it is a complex technology. You need a lot of engineering skills and understanding how things work in order to make batteries that can be safer. Otherwise, really, it can be a dangerous thing. If battery is not designed well, it could have thermal runaway and all the associated problems. So it is not very economic, and that is the reason we do not have many companies in the US. They make the batteries because our manpower is very expensive here. We also do not have the raw materials, and we do not have the technology that we can produce the batteries. So many things we have to really import in order to develop the battery technology, so which is happening now because we did realize our need. So long answer short, yes, there is a need. There are things happening, but it is still not economic.